Hello, this is my lab 2 for Physics 2 over charged tape. The purpose of this lab was to find the charge of the whole tape by modeling the tape as a rod, and we were going to use code to iterate over the length of the tape and break it up into sections, DQ, and find the electrical field and force of the tape. We were going to determine if it is better to model the tape as a point charge or as a rod. And overall, for the findings of this lab, the top tape has a positive charge of 1.91 times 10 to the negative eighth coulombs. The electric and gravitational force of the tape are equivalent in magnitude, and that is 1.99 times 10 to the negative 3 newtons, and it is overall more accurate to model the tape as a rod instead of a point charge. Key concepts for this lab was gravitational force, negative mg, electrical force, which is the electrical field times the charge, and the electrical field of a point charge is kq squared divided by the magnitude of r squared times the direction of r. That would allow you to find the magnitude of the force as well. Um, but more importantly for this lab, we found the electrical field of a rod because the tape was modeled as a rod. And the magnitude of the electrical field is kq divided by r um, times the square root of r squared plus L, the length of the tape, divided by 2 squared. And then we were able to derive that because we know that the force of gravity is equivalent to the electrical force, which will be elaborated on later. But that allowed us to find an equation for charge that we would put into our code, and then the electrical constant. This is the model of the tape. Our system is the top tape, and the surroundings is the bottom tape, which is held with our hands in the earth. The top tape is labeled S2, the green ball in this situation, and the F net is 0 because there's a gravity force acting down and the electrical force acting up. So that was essential in this lab, and each tape has the same net charge. These are just key assumptions. The tape was treated as a rod. We assume the charge was perfectly distributed across the tape and that the atom is a perfect square. And we ignored air resistance on a moving object, which is crucial in this lab. The experiment was we had a bottom tape labeled U and we ripped that fast to create a charge, and then we could find the separation distance as shown to the right. For the code, we have our initial conditions. So these were just the values we had. You can see L and Q. Q was found by using the equation from earlier. Okay, and then the first thing we did was define the E field. So that's a loop that was going, a function that was going. So we found the E field, and we'll use that later on. We defined DQ, which is just separating the tape into even sections. So that way, on the right, we could find the electrical field at each of the DQs, and we could add it to find the total force. And just like, in a sense, doing the integral of that as well. And that allowed us to find the total electric field and electric force and gravitational force as well. And the bottom of the right image is just showing how we demonstrate that. And then important thing to note is E scale and FE scale. These were just modeled so that way the vectors could be seen in an image. Here's the image that was created. The green arrows represent the electrical field, the white is the force electric, and the yellow is the gravitational force. Red is top tape, and then the blue is the bottom tape. Found that the magnitude of electrical force and magnitude of gravitational force are about the same, not entirely the same. And this could just be due to a measurement error. But it was 1.99 times 10 to the negative 3, about. So in conclusion, the top tape has a net force of 0 acting on it, and the tape has a positive charge of 1.91 times 10 to the negative eighth coulombs, which we found in the lab and then by doing calculations. The tape was modeled as a rod and given more accurate numbers than as a point charge, and the computational model is an efficient way to find charge over tape because of the ability to iterate and separate into sections. Possible sources of error could have been the two tapes could have not been entirely parallel during the measurement of the separation distance, so that value could be off. And the model assumes no other outside forces than the one being analyzed. What if the tapes had been modeled as a single point charge? How would the values differ? The equation for a point charge would have been used, which was shown earlier, and this would have impacted the overall charge of the tape. The value would be 2.38 times 10 to the negative 7th coulombs instead of the value we found, and the charge across the whole tape would be 12.46 times greater in that case. The estimations are different because we're assuming the charge is spread across the tape like a rod instead of at a point. So different equations are used and the length of the rod is considered in this case. The value for where the charge is spread across the tape instead of at a singular point would be more accurate because even though the charge may not be evenly spread, it is not just concentrated as a point. It is all over the tape, and that is crucial. Perfect. Thank you.